Welcome back to the Explainer. If you're currently navigating your B.Tech engineering syllabus, especially those JNTUH R25 guidelines, you're going to want to pay close attention today. We're diving into some incredibly cool territory, the practical, real-world behaviors of the PN junction diode. You know, we usually first learn about diodes as these perfect, ideal one-way valves for electricity. But reality? Well, reality is a bit messier, and honestly, a whole lot more interesting. Today, we're unpacking two massive non-idealities: diode resistance and diode capacitance. Getting a solid grip on these is absolutely crucial if you ever want to design actual circuits, from simple power supplies to lightning-fast digital logic.
Okay, let's dive right into this. Here is our roadmap for the Explainer. We'll hit the Shockley diode equation, look at DC and AC resistance, check out equivalent circuit models, and finally, break down depletion and diffusion capacitance.
Section 1. The Shockley diode equation. Because before we can look at the quirks, we really need to understand the baseline steady-state current.
To truly get why a diode acts the way it does, we have to anchor ourselves in the physical reality of the PN junction itself. Imagine joining a P-type and an N-type semiconductor together. Instantly, electrons and holes start diffusing across the gap. But notice that zone right in the middle? That's the depletion region. It's basically wiped completely clean of mobile charge carriers, leaving behind these immobile ions that set up a built-in electric field. It's literally a potential barrier. For electrons and holes to cross and actually create a current, they have to somehow climb over that wall.
And the way we control that wall is through biasing, which is just a fancy way of saying we apply an external voltage. Think of it kind of like flipping a switch. In forward bias, we hook the positive terminal to the P-type side and the negative to the N-type. That external push actively fights the built-in barrier, shrinks the depletion region, and boom, current flows freely. But in reverse bias, we flip the connections. Now the external voltage is actually helping the barrier. The depletion region gets much wider and it totally blocks the current. It basically becomes an open switch, except for a tiny, tiny trickle of leakage current.
Now, all of that physical action is elegantly captured by the Shockley diode equation. It tells us that the diode current, I, equals the saturation current, IS, times a specific exponential factor. Basically, it's the mathematical bridge between the current flowing through the device and the voltage you're applying across its terminals. It even factors in the thermal voltage, which hovers right around 26 millivolts at room temperature, and this thing called the ideality factor, N, which just tweaks the math based on the specific real-world material you happen to be using.
Moving right along to Section 2, DC and AC diode resistance.
And this brilliantly illustrates our very first major curveball. Diodes absolutely do not obey a simple Ohm's law. Because that relationship between current and voltage is exponential, like we just saw, a diode's resistance is actually a moving target. It changes based on the temperature and the voltage you apply. So it behaves totally differently depending on whether you're measuring a single DC point, looking at the average AC resistance over a big voltage swing, or analyzing a tiny AC signal. That average AC resistance, by the way, is a huge deal for large signal analysis. You find it by simply calculating the change in voltage over the change in current, delta V over delta I between two distinct widely spaced points on the curve.
But let's start simple with DC. DC, or static resistance, is exactly what it sounds like. It's the resistance of the diode sitting right there in a stable DC circuit. Super straightforward to calculate. You literally just pick your operating point on the curve and divide the applied voltage by the current. V divided by I. As a general rule of thumb here, the less current you have running through the diode, the higher its static DC resistance is going to be.
So, what happens when we throw small, fluctuating AC signals into the mix? Well, then we need dynamic AC resistance. This is what you use for small signal analysis. To find it, we actually have to use a little calculus and take the derivative of the current with respect to voltage at our specific DC operating point. First, you differentiate the Shockley equation. Then, since conductance is just the change in current over the change in voltage, you invert that result to isolate the resistance. It's a really elegant derivation, and the end result is that dynamic resistance, little rd, is roughly equal to the thermal voltage divided by the forward DC current. The big takeaway here, as your forward current goes up, your dynamic resistance drops right down.
Okay, Section 3, equivalent circuit models. Let's see how this actually looks on paper.
So, how do we practically use all this? I mean, exponential curves and dynamic resistance are great in theory, but they're kind of a nightmare for standard circuit analysis. So we cheat a little bit. We represent our messy, practical PN junction as a perfectly ideal diode bundled with a few extra parasitic elements. It lets us use all our standard linear circuit analysis tricks to figure out what the diode is doing in a much more complex system.
Check out the stark contrast between these two bias states. In the Ford model, we replace the diode with three things in series: an ideal switch, a tiny battery that represents that built-in barrier voltage, and the dynamic resistance, that RD we literally just derived. That whole package perfectly mimics the Ford voltage drop. But look at the reverse model, completely different story. The ideal switch is wide open, but we slap a massive reverse resistance in parallel with it. Why? Just to account for that sneaky little non-ideal leakage current that always manages to get through. Now, what's really interesting about this slide is what we are completely ignoring. We've got resistance mapped out perfectly. But if you drop these exact models into a high-frequency circuit, your math will completely fall apart. Why? Because we haven't accounted for the fact that a diode also acts like a capacitor. That brings us to Section 4, depletion capacitance, specifically under reverse bias.
To uncover this hidden capacitive behavior, we have to look back at the physical junction itself, specifically when it's reverse biased. Remember, under reverse bias, that central depletion region widens out. Now, think about what's actually sitting there physically. You've got a P side full of negative ions, an N side full of positive ions, and right in the dead center, a wide gap with zero mobile charge carriers. Guys, that is literally the exact same physical setup as a standard capacitor, two conductive plates separated by an insulating dielectric.
We call this specific effect depletion or transition capacitance. Mathematically, it's defined by taking the dielectric permittivity of the semiconductor material, multiplying it by the cross-sectional area, and dividing it by the depletion width, W. Now, here's the real kicker. As you crank up that reverse voltage, the depletion with W gets even wider. And since W is on the bottom of our fraction, a higher reverse voltage actually means lower capacitance. It's a voltage-controlled capacitor. That's exactly how engineers designed varactor diodes for radio tuning circuits. Pretty amazing, right?
All right, last piece of the puzzle, Section 5, diffusion capacitance during forward bias.
We know exactly what it does in reverse, but what happens when we flip the switch and go into forward bias? Well, the barrier drops, and suddenly you have a massive flood of charge carriers rushing across the junction. We call this minority carrier charge injection. Electrons dive deep into the P side and holes rush into the N side. But here's the thing, that diffusion isn't instantaneous. It takes time. So while the current is flowing, a huge amount of charge is temporarily stored right outside the depletion zone. And what do we call it when a component dynamically stores charge based on voltage? Yep, capacitance.
This one is known as diffusion capacitance. It basically measures the change in that stored minority charge compared to the change in forward bias voltage. If you look at the formula, diffusion capacitance, or CD, equals the forward current multiplied by the transit time, which is just how long it takes the carriers to cross, divided by the thermal voltage. Because there's just so much charge being injected during forward bias, this diffusion capacitance ends up being way, way larger than the depletion capacitance we just saw in reverse bias. So the crucial point is really perfectly summed up right here in this table. If you're prepping for a B.Tech exam, seriously take a mental screenshot of this. Transition capacitance rules the reverse bias state, and it's totally dependent on the depletion width. Diffusion capacitance takes over in forward bias, it's all about minority carrier transit time, and relatively speaking, it is massively larger. Actually, there's a great quote from the source material that hits the nail on the head. It points out that the Shockley equation is just a steady-state relationship, meaning it completely ignores the diode's transient response, which includes all that internal junction and diffusion capacitance we just talked about. Basically, Shockley is great when things are calm. But if you're designing high-frequency RF circuits or crazy fast-switching logic gates, the voltage is jumping all over the place. And in those scenarios, it's these parasitic capacitances that completely dictate how your diode is going to behave. Which leaves us with a really fascinating question to wrap things up. If high frequencies naturally amplify the chaotic effects of these internal parasitic capacitances, at what exact frequency limit does a standard diode stop being a helpful clean switch and start acting like an impassable roadblock to your signal? It's a huge engineering problem, and it's the exact reason why specialized high-speed diodes exist today. Anyway, that is all for today's explainer. Thanks for hanging out, keep asking those big questions, and I'll catch you in the next one.